So today we continue with Jordan canonical forms. First of all, let me remind you the theorem that we have proved last time about how to get a basis for the whole space consisting of the basis given by union of the basis for the generalized eigenspaces. So this was theorem 7.4 that we proved last time. So the situation here is the following. So as usual, we have a linear operator L on V, where V is a finite dimensional vector space, and the characteristic polynomial of T splits. Okay. Then we let, as usual, lambda 1 through lambda k be the distinct eigenvalues of T. With multiplicities m1 through mk. Okay, so each eigenvalue comes with the corresponding multiplicity. And then for each I between 1 and k, we let beta I be an ordered basis for the generalized eigenspace k lambda I corresponding to lambda I. Then we have the following. So all these bases are disjoint. So meaning that beta I intersection with beta j is empty. For I different from j, this is part A. Part B, if you take the union of beta 1 through beta k, then beta, which is the union of this, is an ordered basis for the whole space V. And finally, part C, we know the dimension of each of the generalized eigenspaces is equal to the multiplicity of the corresponding eigenvalue. So for all I. This is the theorem that we have proved last time. Let me first of all record a corollary of this lemma, which makes it very explicit how this is connected to a diagonalizability. So what happens in the special case when our operator is diagonalizable? And this corollary tells us that nothing new happens, we already know. So namely, if we're in the same situation, so T is a linear operator on V, the dimension of the space is finite, and the characteristic polynomial of T splits, then we have that the linear operator T is diagonalizable if and only if we have that each of the generalized eigenspaces k lambda is equal to the usual eigenspace E lambda for every lambda an eigenvalue of T. Okay, so we have yet another criterion for diagonalizability of a linear operator. Namely, we have that it's diagonalizable if and only if the generalized eigenspaces are just the usual eigenspaces. So the proof of this follows from the theorem. So let's see. We know by the theorem we just recalled, so theorem 7.4, and also by an earlier theorem 5.9 about diagonalizability. So we know that a linear operator T is diagonalizable if and only if the dimension of E lambda is equal to the corresponding multiplicity of this eigenvalue lambda, which by 7.4 again is exactly the dimension of the generalized eigenspace k lambda for each eigenvalue lambda of T. Okay, so remember, again, here I'm combining two facts. So this is 7.4 and this is 5.9. So 5.9 tells us that a linear operator is diagonalizable if and only if the dimension of every eigenspace is equal to the multiplicity of the corresponding eigenvalue, right? And by the previous result, by this theorem 7.4 here, we know that we get the second equality. So combining these two facts, we have that T is diagonalizable if and only if the dimension of E lambda is equal to the dimension of K lambda. But we also know that E lambda is a subset of K lambda. So remember, we proved this earlier. And they have the same dimension, right? So the equality E lambda is equal to K lambda happens if and only if the dimensions are the same. So the dimension of E lambda is equal to the dimension of K lambda. And from these equivalences, we get the corollary. So T is diagonalizable if and only if the dimensions are equal. So the dimension of E lambda is equal to the dimension of K lambda. And this happens if and only if E lambda is equal to K lambda. And so this gives us the corollary. Okay, everyone is fine with this? Okay, so our next aim is now to connect generalized eigenspaces to the Jordan canonical form of an operator. Roughly speaking, the logic here is going to be the same as when we proved that diagonalizability, or saying that the matrix of linear operators diagonal is equivalent to having an eigenbasis consisting of, having a basis consisting of eigenvectors. So here we are trying to get something similar for Jordan canonical form, but instead of the usual eigenvectors, we have to use generalized eigenvectors of special form. So we are trying basically to develop a general method for finding a Jordan canonical basis for an operator. Now, in view of this theorem, theorem 7.4, we first should learn how to select a suitable basis for generalized eigenspaces. So let me make a definition towards that purpose. So assume that T is a linear operator on V, and let X be a generalized eigenvector of T corresponding to the eigenvalue lambda in F. Okay, so fix a generalized eigenvector X and suppose that P is a positive integer which is the smallest, such that we have T minus lambda I to the power P evaluated on X is equal to 0. So why does it exist? Well, because it is a generalized eigenvector, we know that some P like this must exist, right? This is equivalent to being a generalized eigenvector. This is equivalent to saying that for some P, we have this holds. So then we just fix the smallest P satisfying this. All right. Then the ordered set consisting of the vectors T minus lambda I P minus 1 of X, T minus lambda I P minus 2 of X, etc., ending in T minus lambda I of X and X itself. So this ordered set is called a cycle of generalized eigenvectors of T corresponding to lambda. Okay, a cycle of generalized eigenvectors of T corresponding to lambda. And we take it in this order. So the first vector in it is given by the power p minus 1 of x. So first of all, note each of this is a vector in V. So this is a subset of V. Moreover, it's actually a subset of k lambda. So this is a subset of k lambda. So why this true? Well, because by assumption, P, remember, P is such that this is equal to 0. So T minus lambda I to the power P of x is equal to 0. But then if I look at this vector, it means that T minus lambda I applied to this vector is 0. So this means that this is in k lambda. Similarly for this one, we have that T minus lambda I to the power 2 applied to this vector is equal to 0, etc. So each of these vectors is in fact in k lambda. Yeah, so they're all generalized eigenvectors. That's why in the name we have that this is a cycle of generalized eigenvectors. And they're all obtained by applying the operator again and again, p minus 1 times. Okay, so this is just a definition. And we also will have special names for the first vector in this ordered set and for the last vector. So the vector T minus lambda I to the power p minus 1 of x and the vector x are called the initial vector and the end vector of this cycle. Okay, respectively. So we have the initial vector, which is this one, and we have the end vector, which is just x itself. And finally, the length of the cycle is p. Okay, so we have this special kind of cycles of generalized eigenvectors corresponding to a given eigenvalue. Let's first make a couple of remarks about this new object that we just defined. So remark 1, the initial vector is the only eigenvector of T in the cycle. So why this? Let's go back to the definition for a second. So first of all, like we said, every element of the cycle is a generalized eigenvector because they're all in k lambda. But only one of them is an actual eigenvector rather than just a generalized eigenvector. And this is the first one, right? Because if I look at this vector and I apply T minus lambda I to this vector, then what I get is T minus lambda I to the power P of x, right? And by assumption on P, this is 0. So this tells me that this is indeed an eigenvector. Okay, so this is part 1. And part 2, if x is an eigenvector of T corresponding to lambda, then the set consisting of the single vector x is a cycle of generalized eigenvectors of T corresponding to lambda of length 1. Okay. So the point of this cycle is that we start with a generalized eigenvector, then we apply the operator to it, p minus 1 times, and eventually we get an actual eigenvector for T. Yeah. But if you start already with x, an eigenvector of t, then there's no point of applying the operator any further, because then we already know that t minus lambda I of x is equal to 0. So it works with p equal to 1. So we get in this case, we get a generalized eigenvector. Sorry, we get a cycle of generalized eigenvectors, which is just of length 1. All right. So we have this new notion. So now let's see how this the cycles of generalized eigenvectors, how they are connected to Jordan blocks. So this is going to be the content of theorem 7.5. Let T be a linear operator on V, where V is as usual finite dimensional, and the characteristic polynomial of T splits. And suppose that beta is a basis for V, ordered basis for V, such that beta is a disjoint union of cycles of generalized eigenvectors of T. Then we have the following two properties. A, for each cycle gamma of generalized eigenvectors contained in beta, if we let W be the span of gamma, then this subspace W is T invariant. And if we look at the matrix representing T restricted to W with respect to gamma, then this matrix is a Jordan block. This is part A, and part B, beta, is a Jordan canonical basis for V. So the theorem basically tells us how to find a Jordan canonical basis. If we are able to find a basis which is a disjoint union of cycles of generalized eigenvectors, then each of these cycles gives us a Jordan block, and the union gives us a Jordan basis for, this should say for T, not, well, Jordan canonical basis for T. I mean, it's a basis for V, but corresponding to the linear operator T. Okay, does the statement of the theorem make sense? First of all, let me pause for a second. So the theorem gives us a recipe how to find the Jordan canonical basis. Namely, we need to find all the generalized eigenspaces. Then inside each of them, we want to find a cycle which gives a basis for the corresponding subspace W, the span of gamma, and then the union is going to be a Jordan canonical basis for V. Okay, so let's prove this. So let's first prove A. So suppose that gamma, a cycle inside beta, a subset of beta, which is a cycle of generalized eigenvectors, corresponding to lambda, to an eigenvalue lambda. And suppose that this cycle gamma has length p for some p. And suppose that x is the nth vector of gamma. Okay, so since it's a cycle, it makes sense to talk about all of this. Then we can write gamma as follows. So we can write it as the vectors v1 through vp, where we have that each vi is equal to t minus lambda I to the power p minus I applied to x for I less than p, and the end vector vp is just x. So here I'm just copying the definition, right? I'm just looking at the definition of a cycle here. So we have a cycle and the end vector is x. So then I just wrote it out. It's a cycle with end vector x and of length p. So then it means the end vector is x, and each of the previous vectors vi is given by the corresponding expression. So here the power is p minus I for the ith vector. Okay, but then if we look at t minus lambda I and apply it to v1, then what we get is t minus lambda I composed with t minus lambda I p minus 1 applied to x. So this is simply t minus lambda I to the power p applied to x, and this is 0, right? Because p is the length of the cycle and x is the end vector. So by assumption, this is equal to 0. Okay, hence we have that t of v1 is equal to lambda v1, right? Because if I have that t minus lambda I applied to v1 is equal to 0, from this equation we can express t of v1. This is going to be simply lambda v1. And similarly, we can argue for I greater than 1. If we look at t minus lambda I applied to the vector vi, this is going to be t minus lambda I to the power p minus I minus 1 applied to x. But then this is going to be v I minus 1. And so we get that t of vi is equal to v I minus 1 plus lambda vi. And note that this is an element of w, because w is the span of gamma. And the vectors vi are all in gamma. So we get that t of vi is an element of w. And let's denote this equality by star. Okay. Any questions about this derivation so far? Okay. If not, so the point of what we just demonstrated is that T maps W into itself, right? Because if I start with any of the vectors Vi in the basis for W, because W is the span of gamma, so if I apply T to any of the vectors in the basis, I get some vector which is still in the span, right? So then it means that it means that this subspace W is T invariant. So W is T invariant. Okay, we have this. And also, let's look at the matrix representing TW with respect to gamma. So we have that the matrix representing TW with respect to gamma, because what are the columns of this? Well, they're given, right? We have, they're all given by star. So using star, we can write the columns one by one. So for the first column, we simply get lambda, and then we have zeros below it. Let me write it like this. For the second column, we have 1, right? Because I'm just applying, look at T of V2. T of V2, if we apply star, it is given by v1 plus lambda v2. So it means 1, then I have lambda, and then I have zeros. And continuing this way for each column, we get that we have lambda on the diagonal, we have 1 above it, and we have zeros everywhere else. And so this is a Jordan canonical block, or a Jordan block. So we see that the matrix representing T W, so restricted to this subspace, is a Jordan canonical block. All right. And now how to get part B? So part B of the theorem says that beta is a Jordan canonical base for T. So I'm not going to write it in full detail, but what we have is that repeating the argument of A for each cycle in beta. For each cycle in beta. Okay, so we get that restriction to each cycle, span of each of the cycles is a Jordan block. And then if beta is a basis, which is union of those, then we know that the matrix representing it is going to be a Jordan canonical form, because it's going to be a direct sum of the matrices for each of these TWs, but each of those is a Jordan block. So we're going to get that the matrix representing T with respect to beta is the direct sum of the matrices which are Jordan blocks. And so this means that the whole matrix for T is a Jordan canonical form. All right, so that's the logic here. So in view of this result, let me summarize where we have arrived so far. So in view of this result, to find a Jordan canonical basis, we must show that there exist bases that are disjoint unions of cycles of generalized eigenvectors. Right, so that's what the theorem is telling us. If we can find a basis which is given by union, or more precisely, disjoint union of cycles of generalized eigenvectors, then we can find a Jordan canonical basis for the operator T. Now, also one can observe that since the characteristic polynomial of a Jordan canonical form splits, so this is a point that appears on the homework, this is also a necessary condition. So our aim is then to show that this is a sufficient condition as well, just that the characteristic polynomial splits. Okay, so we're going to work now towards that, to show that if we're given an operator whose characteristic polynomial splits, then indeed we can find a basis consisting of generalized disjoint union of generalized cycles. Okay, so next task is to show that if the characteristic polynomial of T splits, then such basis, as described here, exists. So that's our task. We need to find, to demonstrate that we can always find a basis of this form, assuming that the characteristic polynomial splits. So let's, okay, so this takes a bit of work. The first result that we need is theorem 7.6 towards this purpose. So the situation is as usual. T is a linear operator on V, and let lambda be an eigenvalue of T. And suppose that gamma 1 through gamma q for some number q are cycles of generalized eigenvectors of T corresponding to lambda, such that, moreover, the initial vectors of these cycles of the gamma i's are distinct and form a linearly independent set. Right. So this is the assumption. For a fixed eigenvalue lambda of T, we have some cycles, gamma 1 through gamma q, of generalized eigenvectors corresponding to this eigenvalue lambda, so that for each of them, we can pick the initial vector. Remember, from the definition of a cycle, we can pick the initial vector, and we assume that just these initial vectors are independent, are linearly independent. Then we can conclude that the cycles gamma I are disjoint, and if we take gamma to be the union of gamma I for I from 1 to q, then this whole set is also linearly independent. So we are only assuming that the initial vectors are linearly independent, but from this we can conclude that all vectors in the union of the cycles are in fact linearly independent. Proof. So first of all, the fact that the gamma I are disjoint we leave it as an exercise. So it appears in the homework 9, which, remember, is optional, but I encourage you to actually try to figure this out. So this I would just claim for now that these cycles are disjoint. So the next task is to show that then the union gamma, the union of the gamma I for I from 1 through q, is linearly independent. Okay. So this is what we want to show. In order to show this, we are going to argue by induction on the number of vectors in gamma, on the size of gamma. So by induction on the number of vectors in gamma. So first of all, if we have that the size of gamma is less than 2, then this is clear, because in this case gamma is simply has size 1 or 0, and in either of these cases, remember that vectors, which are any vector in k lambda, is non-zero. Not in k lambda, excuse me, any generalized eigenvector is non-zero. But of course, if I just give you a single non-zero vector, then the set consisting of this single vector is automatically linearly independent. So the base step is automatic. So then for the inductive step, we assume that gamma has cardinality n greater or equal than 2. And we assume that the result holds for gamma less than n, the cardinality of gamma less than n, the size of gamma. All right. So now we need to show that gamma is a linearly independent set. So the idea is, as usual, when we want to use the inductive assumption, we have to find some smaller dimensional, some subspace on which we have smaller size of the union of cycles. So towards this purpose, we let W be the span of gamma. Okay, we take W to be the span of gamma. Then observe that W is T minus lambda I invariant subspace of V. So this we have simply by the definition of a cycle. Yeah, because remember how we get a cycle. Cycle has the nth vector x, and then if you apply T minus lambda I to it, we get the next element in the cycle. You apply it again, you get the next element until you get 0. But then if you pick any element in the cycle and apply T minus lambda I to it, you either get 0 or the next element in the cycle. And this is cycle is the basis of W. So we see that applying T minus lambda I to any vector in this basis for W gives us some vector which is still in the span of gamma. So it follows that W is T minus lambda I invariant. Now let us take U to be T minus lambda I, the linear operator T minus lambda I, restricted to this subspace W, which makes sense because we just remarked that it is in an invariant subspace, in fact. Okay. Now, for each I, we let gamma I prime be the cycle obtained from gamma I by deleting the nth vector So if we have that the size of gamma I is equal to 1, then gamma I prime is going to be empty. Because if I delete the single vector from gamma I, I'm going to be left with nothing. Yeah, so it's gamma I prime is going to be empty in this case. And if gamma I prime is not empty, then each vector of gamma I prime is the image under U of a vector in gamma I. Right? Because I only deleted the nth vector. And so every other vector is obtained by applying U several times to the nth vector. But the nth vector is in gamma I, and so, and as well as all the other vectors in the cycle. So we get that each vector of gamma I prime is obtained by applying Q to some vector in gamma I. All right. So we have this, and conversely, we have that every non-zero image under U of a vector in gamma I is contained in gamma I prime. So we have these two simple observations connecting gamma I and gamma I prime, which follow simply from the definition. So gamma I prime is obtained by removing a single vector, the nth vector from gamma I. And we let gamma prime be the union of gamma I prime for I from 1 through Q. Then by star, so given these two conditions here, star, we have that gamma prime generates the range of U. Gamma prime generates the range of U. So we have this. All right. So also we have that the size of gamma prime is going to be n minus q. So how do we get this? Well, because gamma prime, remember, it's the union of gamma I prime, but each gamma I prime has the size which is the same as the size of gamma I minus 1, because we are removing a single vector, the nth vector of gamma I. And since there are q of them, this is how we get that this is n minus q. Okay. So we have this estimate for the size of gamma prime, and the initial vector of gamma I prime is the same as the initial vector of gamma I. So this is the initial vector of gamma I for all I between 1 and q. So we didn't change the initial vectors because all we did is remove the nth vector from each gamma I. Okay. So by the induction hypothesis, we have that gamma prime is linearly independent, right? Because we have, look, we have the same situation. Each gamma prime is a cycle for U, and the initial vectors are linearly independent because they're the same as the initial vectors of the gamma i's, which were linearly independent by assumption. So they're linearly independent, hence all of gamma prime, the union, is also linearly independent by applying the theorem to the case when the cardinality of gamma prime is smaller than n, because we assume that it holds for every size of the union of the cycles smaller than n. All right, so it is linearly independent. So we have two things. It is linearly independent and it generates the range of U. So we conclude that gamma prime is a basis for the range of U, right? So we get that gamma prime is a basis for the range of U. Hence, we have that the dimension of the range of U is also equal to n minus q, right? So we get the same dimension for the range. And since we also have that the q initial vectors of the gamma i's form a linearly independent set by assumption, and lie in the null space of U. Yeah, because remember the initial vector, if you apply U to it once again, we get 0. So they lie in the null space of U. We conclude that we have that the dimension of the null space of U is greater or equal than Q. So this is by the rank nullity theorem. Right, because we have that this dimension of the whole space is n. The dimension of the range is n minus q. So the dimension of the null space is then we get at least Q. All right. So again, in fact, sorry, this is not even the rank nullity yet. This is just because we have Q vectors which are linearly independent and they're all in the null space. I'm sorry, I'm running a bit ahead of myself. So this is simply because we have Q linearly independent vectors which are all in the null space, right? Yeah, this is not using anything. We just know that we have Q linearly independent vectors all contained in the null space of U. So the dimension of U of the null space of U is at least Q. But now we can use the rank nullity theorem here. So by rank nullity theorem, we get that n greater or equal than the dimension of W, which is the dimension of the range of U, plus the dimension of the null space of U. So this is greater or equal than n minus Q plus Q. But this is, of course, just n. Right? So we get that n is greater or equal than the dimension of W. And in turn, this is greater or equal than n. So this tells us that the dimension of W is, in fact, n. Because it's both greater or equal and less or equal than n. So it is equal to n. All right, so we get the dimension of W as n. And we also have that W is the span of gamma. And the size of gamma is n. So it follows that gamma is a basis for W, right? Because the dimension of W is n, and we have found a subset gamma which generates W and has the same cardinality. So then it automatically must be linearly independent. So it is a basis for W. Okay, so in particular, linearly independent. And this is what we wanted to show. We wanted to show that gamma is linearly independent. Okay. So again, yeah, there was a couple of steps in this proof, but the main idea was to look at the given collection of cycles, remove the nth vector from each of them, and show that we still get a collection of cycles for the operator U this time, and so to which we can apply the inductive hypothesis. And let me end with a quick corollary of this result. So we have that every cycle of generalized eigenvectors of a linear operator is linearly independent. Okay, so this corollary is immediate from the theorem, simply by looking at the case when we just have one cycle and the initial vector of the cycle is not zero, hence it is automatically linearly independent. The set consisting of a single non-zero vector is automatically linearly independent. And so it follows the whole cycle of generalized eigenvectors is linearly independent. Okay, so this is a corollary of the theorem applied to the situation when we just considering a single cycle of generalized eigenvectors. So I'll stop here. Next time we'll see how to, well, next time we'll connect all of this and see how to get a Jordan canonical form in the case when the characteristic polynomial splits, which is the ultimate aim of what we are trying to do here. All right, so I'll stop here. Thank you very much. Let me know if you have any questions. Thank you. All right. See you. Bye-bye.